In this question, we intend to simulate a simple example having been selected about the strength of materials in the Abaqus software and compare the results obtained from the Abaqus software with those gained about the subject of the strength of materials. In this picture, you can observe the problem statement in which two steel and aluminum bars have been connected together and a force of 20 kilonewtons is applied to the aluminum bar. The purpose of this problem is to calculate the displacement of points B and C. In this training video, we solve this problem once using the Abaqus software and once the problem is solved benefiting from the strength of materials, and the results of both are compared together subsequently. I will enter the Abaqus software for simulation. I will click on Create Part. I intend to create a geometric shape of the bar. Here, I will select the modeling space as 3D, deformable. From here, select Wire and Planar. Enter approximate size equal to 5 and continue. I will draw a horizontal line. As you observe in this picture, the whole length of the bar is equal to 2 meters. I'll then click on Done. In the next step, we should create a partition over the bars so that the steel bar would become distinguished from the aluminum one. I will click on Tools menu, select Partition, from here Edge, and then select Midpoint, Datum Point. Select this point located at the center of the bar and click on Create Partition. In the next step, I will enter Property module. Click on Create Material. Here, I intend to define the properties of steel. I will click on Mechanical menu, then select Elasticity and Elastic. As you observe, the Young modulus of steel is equal to 200 gigapascal. I will enter that equal to 200 multiplied by 10 to the power of 9 Pascal, and the Poisson ratio is equal to 0.3. Okay. I will click on Create Material again. I intend to define the properties of aluminum. I will click on Mechanical menu, select Elasticity and Elastic. The Young modulus of aluminum is equal to 70 gigapascal. Poisson ratio is equal to 0.33 and OK. In the next step, I'll click on Create Section. Here select Beam and then Truss. In this question, we have considered the type of elements as truss. Of course, there will be no problem even if we use beam elements here, since the results obtained from the beam are the same as those gained from the truss. Here I will select Truss, continue. Here select Steel Materials. The cross section of steel is equal to 4 multiplied by 10 to the power of negative 4 square meters. And OK. I will click on Create Section again. Here select Beam and then Truss and continue. I will select Aluminum material. The cross section of aluminum is equal to 2 multiplied by 10 to the power of negative 4 square meters. I will click on Assign Section, select the left bar that is related to Steel, done. Select Steel section and OK. I will select the right bar that is related to Aluminum, done. Select Aluminum section and OK. Here you can observe the three-dimensional form of the bar. In the next step, I will enter assembly module. Click on Create Instance. OK. I will enter time period equal to 1 second. The nature of this question is linear, so I will select off option. But even if you select on, it will be okay, and the results obtained don't make any difference together. Anyhow, here I will select off option because the problem is linear indeed. Okay. Click on Create Boundary Condition, select Displacement, Rotation, and continue. I will select the end of the bar, done, and close all boundary conditions of displacement. Actually, as you observe in this picture, the left end of the bar is absolutely fixed. In the next step, I will click on Create Load, select Step 1, then Concentrated Force, and continue. I will select this point, done. The force is equal to 20 kilonewton, so I will enter the quantity of force equal to 20,000 newton. Put a negative sign here and OK. As you observe, the direction of the force is to the left. In the next step, I will enter Mesh module. Click on Seed Part, enter approximate global size equal to 0.01 meters. Click on Mesh Part and yes. In the next step, I'll click on Assign Element Type. Select the whole of the bar, done. Put the element family on truss and OK. In the next step, I will enter Step module. Click on Tools menu, then select Set and Create. I will name the set point B. Continue. Select this node. Done. In the next step, I will click on Tools menu, then select Set and Create. Name this set point C. Continue. Select this point. Done. I will click on Create History Output. Continue. Here, select Set, then point B. I will select U1 and OK. I will click on Create History Output. Continue. Here I will select Set and then point C. Here select U1 and OK. I will enter job module here. I will save the model. I will click on create job. Continue. OK, and click on submit. The analysis was done successfully, so I will click on result. The goal of solving this problem is to obtain the horizontal displacement of points B and C. Here we are going to solve this question using the strength of materials. Here the basic formula and relations of strength of materials knowledge have been benefited from in order to solve this problem. Of course, you are certainly familiar with these formulae, but I will explain about them here. First, you observe the stress formula. It is equal to force divided by area. In the next step, you observe the Young modulus formula. It is equal to stress divided by strain. Finally, you observe the strain formula, and it is equal to change in length divided by the initial length. If you simplify these formulae, you will get the formula. Delta X is equal to FL divided by EA, and we use that for calculating the change of length. Here, first, the change in length of the steel, or the same displacement of point B has been calculated. Here, F stands for force, L stands for the length of steel, E is the Young modulus of steel, and A is the cross-section of steel rod. As you observe, the displacement of point B is equal to 0.25 multiplied by 10 to the power of negative 3 meters. Actually, this result has been obtained through using the strength of materials formulae. Now, we intend to calculate displacement of point B using the Abaqus software. First, I will click on Create XY Data, select ODB History, Output, and Continue. Here I will select the displacement of point B and click on Save As. As you observe, the horizontal displacement of point B is equal to 0.00025 meters, or the same 25 multiplied by 10 to the power of negative 3 meters. As it can be observed, the result obtained from the Abaqus software is exactly in conformity with the analytical solution. Actually, the result obtained from the strength of materials are in quite conformity with those gained from the Abaqus software. In the next step, we will calculate the change in the length of aluminum, the formula of which can be observed here. In order to calculate displacement of C points, we should add the change in the length of steel to that of aluminum. Here, displacement of point C has already been calculated, and that is equal to 1.6785 multiplied by 10 to the power of negative 3 meters. Now we intend to calculate displacement of point C using the Abaqus software and compare the results gained from the Abaqus software with those related to the strength of material. I will click on Create XY Data, select ODB History Output and continue. Here I will select point C and click on Save As. Here the displacement of point C is equal to 0.0016785 meters. Actually, the displacement of point C obtained from the strength of materials is equal to 1.6785 multiplied by 10 to the power of negative 3 meters, and the displacement having been gained from the Abaqus software is equal to 0.0016785 meters. As it can be observed, the results obtained from the Abaqus software are in conformity with those inferred from the analytical solution. Here you can also observe the horizontal displacements of various points.